Hey, welcome back to Math with Patrick. Today is September 22nd, and we're solving problem 265 from the Daily Epsilon calendar. And we need to show why the answer today is 22 because that matches today's date. So we need to find the number of regular polygons with interior degree or integer degree interior angles. So regular polygons are just like shapes that are closed, and then the sides and angles need to all be congruent to each other. So for example, like an equilateral triangle is a regular polygon because all these sides and angles are congruent. But something like a rhombus is not a regular polygon because even though we do have congruent sides, these angles are not all congruent to each other. So if we did want a regular polygon with four sides or a regular quadrilateral, that's just our square. And so we basically need to work our way up the polygons from 3 sides to 4 sides to however many sides we need to solve this problem and figure out which ones and how many of them have integer degree interior angles. That just means that we have some kind of whole number right here and here. And like for a pentagon, maybe we're going to have whole numbers, in these spots for those angles. So let's just explore a few of our regular polygons just to see what happens. Let's see. One way that we can prove the angles, the interior angles of a equilateral triangle is, maybe you could trust me that if we build a regular hexagon, we're just going to make it out of just 6 equilateral triangles. And then if all the way around the circle is 360 degrees, then we can divide that by 6 because there are 6 triangles to get 60 degrees for any one of these 6 spots in the middle. So that's one explanation, I suppose. The other one comes from the idea that, like with any triangle, the sum of the interior angles is 180 degrees. I think that one follows from some kind of parallel line proof, where if we draw a triangle here, and I'm just trying to pick kind of like random length sides here so it can be generalized for any triangle. If we look at these 3 angles right here, those make a straight line, and so clearly those 3 angles added up are going to create a 180 degree, angle together. It's basically just a half turn of a circle, or 180 degrees. And then we could use the interior angle theorem, or whatever it's called, or the alternate interior angle theorem, where when we have angles on the inside of these parallel lines, so interior angles, and when they are alternate or on alternate sides of this diagonal right here, or the transversal, they are going to be congruent. So these 2 angles right here have the same measure, and then this angle and this angle are going to have the same measure as well, just because they are alternate interior angles. So if you believe me that these 3 added up are going to be 180 degrees, then you should also believe that the 3 interior angles of the triangle add up to 180 degrees. And this 180 is important for the rest of our polygons. Let me just note it here that the sum is going to be 180 degrees. And then so down here, we get 60 degrees for each of the 3 angles. This 180 is important because as we look towards our square, we could just divide it into 2 triangles. And so these angles all added up are going to be equal to 180 degrees. And then this angle and this angle and this angle are all going to add up to 180 degrees. And so overall, I've just traced out all 4 sides of the triangle. And so therefore, it is 180 degrees plus 180 degrees, which has a sum of 360 degrees. Or it could have been pretty obvious that these are all 90 degree right angles. And so just doing 90 times 4 is 360, or 360 divided by 4 for the 4 angles gives us 90 degrees. I just wanted to show many different ways to show that, yes, we do have 360 degrees when we add up the interior angles of a square. And then yes, we do get 90 degrees for each individual interior angle. So this pattern of adding up a bunch of triangles, though, is going to help us with our pentagon, because here we could draw two triangles like this. Each of these triangles, we're going to add up this, 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 that, that, and that. It's essentially 3 times 180 for the entire sum of all those angles added up together. That's going to be 540. And then when we divide that by 5, we are going to get 108. And so this is yet another integer degree interior angle. I think let's get the hexagon on there because we did draw it earlier. So we can get a regular hexagon here. And since regular hexagons are just made up of 6 regular triangles or equilateral triangles, we can add the 60 and the 60 to get 120 for the interior angle there. And then multiplying that by 6, we do get 720. And then also we can still use the idea of adding 180 degrees to go from one polygon to the next. So now we have some kind of like general formula essentially to find these numbers. Essentially, we just need to do 180 times some amount of triangles, and then we're going to divide it by the amount of sides we have. So we have number of sides down here and number of triangles up here. Like for this hexagon, we had not 6 triangles, right? Because we would need to draw it kind of all emanating from the same corner. So we would have 4 triangles right there for a 6-sided shape. If we wanted to try it with a pentagon, we had 3 triangles for a 5-sided shape. And so essentially, if we have, say, n number of sides, we're always going to have n minus 2 number of triangles that form our regular polygon. So this expression right here is equal to all of these numbers when n is equal to the number of sides we have for our polygon. So I'll just say n is equal to number of sides. Now we just need to figure out when this fraction right here is an integer. So I'll just say like is an element of the integers like that. And I think the best way to do this is to like break up this 180 into its factors. So like 180 is the same thing as like 90 times 2, 90 is 9 times 10, 9 is 3 and 3, 10 is 2 and 5. So we can take a look at this fraction and think of it as n minus 2 times 2 times 2 times 3 times 3 times 5. Then we're dividing this by n still. So I want to know when this fraction is an integer, and essentially we just need to be able to cancel this n with one of these factors up top. And I want to ignore the n minus 2 for just a bit, because essentially we're just trying to find the number of factors of 180. Because like if I put any number that divides 180, well, this number right here is the number 180. And I know how to create factors out of numbers, knowing their prime factorization here. Essentially, if we wanted to create something that could divide 180, all we got to do is figure out how many 2's that we're going to bring in. Either we bring in none of them, one of them, or 2 of them. How many 3's, we could pick none of them, one of them, or 2 of them. And then we can decide whether or not to include the 5. So we either have 0 5's or 1 5. And so I have 3 options for the number of 2's I have, 0, 1, or 2. 3 options for the number of 3's, and 2 options for the number of 5's. And if I multiply these 3 numbers together, I will get the number of factors or divisors of 180. This right here is 18, though, and the answer for today's problem is 22. So it looks like I'm missing 4 potential answers here to this problem. So I do need to figure out what is going on here. And so if we try out a few numbers, right, like we already know that we're starting at n equals 3. So then we'd have a 1 here and a 3 down here. So it's not like I'm canceling the 3 with this 1. I'd be canceling this 3 with one of the already pre-existing 3's. When n is 4, this is a 2. And so I could, I guess, cross off these two. And now I'm actually using that n minus 2 right there. But I didn't really need it because I could have just crossed off the existing 2's that were already there from 180. And then I'm seeing anytime that we have an odd number here, these are never going to cancel each other. These two numbers are always 2 apart. So really the only chance that we're going to find a common factor between these two numbers is if that common factor is a 2, right? Because if I pick any odd number, these are just going to be too far apart to have any hope of having a common factor. But then any even number pair, if I put 10 here, then I'll put 8 here. So I could cross off one of the 2's from here with one of the 2's on top. So I think what that lets me do is that this n on bottom could be, it could be even, of course, because we have a lot of examples of when it's even. But this n right here could have one more 2 than 180. Because, let's take a look at, say, 360, right? That would just be the number where we tack on one more 2 than all the factors in 180. We would just get 180 times 2. This is the number 360. This number right here would need to be 358. And since it's even, this extra 2 would cross off with whatever 2 is hiding in 358. So it's actually not that I had 2 2's to play around with, but rather I had 3. This number down here, this n, which represents the number of sides of our polygon, could possibly have 3 2's in it, and we would still be able to cancel out that third 2 with this extra factor on top. So that changes this 3 to a 4. 4 times 3 times 2 is 24. So now I have 24 possible numbers that could go down here. The answer is still 22 for today, so I'm overcounted by 2. Earlier, though, I did say that n equals 3 is the smallest possible value for n, and this strategy right here is accounting for the numbers 1 and 2. The number 1 is right here where I pick, no 2's, no 3's, and no 5's. That's the number 1. And then I also have the option here to pick 1, 2, no 3's, and no 5's. That's just the number 2. But then if I try to make another small number by grabbing no 2's, just 1, 3, and then no 5's, well, this is just our triangle example, and I know that we're allowed to do that. So I do need to subtract from my 24 2, just because this accounts for our one-sided and two-sided polygons, which don't really exist. Because 1 and 2 definitely will divide whatever's going on in the numerator here. But then, if we put a 2 right here, we would actually get 0 on top. That's kind of strange. And then if we put a 1 on bottom, we would get a -1 on top. Also kind of strange. So it's really important that we start at n equals 3 and go up. And so for that reason, I'm discounting n equals 1 and n equals 2 by subtracting 2. So that gives us 22. It gives us a strategy to generate all 22 numbers. I don't really care for actually writing them all out. But now we know that it's basically just factors of 360 that aren't 1 and 2. So that's our answer. That's how you get the 22. And I think we're all done. So thank you for watching. I'll see you tomorrow. Bye.